going to talk about acids and bases. Now, acids and bases are defined in several different ways. Arrhenius acids and bases, which have some limitations, Lewis acids and bases, which are used a lot in organic chemistry, and Bronsted-Lowry acids and bases, and this is the one we need to know about for AP chemistry. The Bronsted-Lowry theory describes acid-base interactions in terms of proton transfer between chemical species. And when we say proton, we mean an H+ ion, a hydrogen that has lost its electron. A Bronsted-Lowry acid is any species that can donate a proton. Such a species must have a proton, an H+, that can dissociate. A Bronsted-Lowry base is any species that can accept a proton. Such a species must have at least one lone pair of electrons that can accept a proton. The Bronsted-Lowry definition can be applied to reactions in any solvent. It can also be applied to acid-base reactions that can happen in the gas phase, which sometimes happens. Here's an example of one acid-base reaction, and we have ammonia, and it's reacting with hydrochloric acid, and it is forming this compound over here, ammonium chloride. So, how to identify Bronsted-Lowry acids and bases? Well, the acid gives away a proton and the base accepts a proton. You could also say that the acid gives away a hydrogen ion and the base accepts the hydrogen ion. So here's an example. We have nitric acid and we're putting it into water. The nitric acid is a Bronsted-Lowry acid and it donates a proton. The water is a Bronsted-Lowry base and it accepts a proton. Here's another example. We have ammonia and it's reacting with water to make ammonium and hydroxide. The water is a Bronsted-Lowry acid because it donates a proton. The ammonia is a Bronsted-Lowry base and it accepts a proton. Since water is capable of donating protons or accepting them, it can act as an acid in some cases and as a base in others. And we say that it is amphoteric or amphiprotic. Now let's do a reality check. Let's talk about H+. Let's talk about those protons. Even though we often write equations with the term H+ in them, there really are no free H+ ions floating around in aqueous solutions. Instead, hydrogens like to hang out with water molecules to form hydronium ions. The hydrogen can attach itself to one of the lone pairs on the water molecule, like this. We have our hydrogen ion or proton, and it will combine with the water molecule to make hydronium, H3O+. Hydronium ions form almost immediately when an acid dissociates in water. So, although we sometimes use H+ in our equations, H3O+ is really more of an accurate representation of what's going on. Now let's talk about acid strength. Strong acids are acids that dissociate completely into their constituent ions in aqueous solution. This means they ionize 100%. A weak acid is an acid that does not dissociate completely in aqueous solution. It only dissociates partially. Often you'll see weak acid dissociation shown as an equilibrium reaction like this one. In this particular reaction, we see that there's a significant concentration of the acetic acid molecules as well as the dissociated ions. Hence, the acetic acid has not completely dissociated. It's dissociated just a little bit. There are only a few strong acids, and everything else is a weak acid. Here are the strong acids you need to memorize: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. Now for bases, strong bases ionize completely in aqueous solution. For example, sodium hydroxide will break into sodium ions and hydroxide anions. Weak bases only partially ionize. You often get a dynamic equilibrium. In this reaction, there's a significant concentration of the ammonia molecules as well as the dissociated ions. Common strong bases are all of the group 1 hydroxides like sodium hydroxide and potassium hydroxide and lithium hydroxide. Also the group 2 hydroxides with calcium and strontium and barium. And there are some others. Now let's talk about conjugate acid-base pairs. When an acid donates a proton, the species that remains is called a conjugate base. When a base accepts a proton, it is converted into a conjugate acid. Conjugate acids and conjugate bases come in pairs. They essentially have the same formula, though the conjugate acid has an extra H attached to it. So let's take a look at this reaction here. Our Bronsted-Lowry acid is the hydrochloric acid. Once it gives away its proton, it becomes a chloride ion, and that is the conjugate base of hydrochloric acid. Likewise, water will accept a proton. Water acts as our Bronsted-Lowry base, and after it accepts a proton, it becomes the conjugate acid hydronium. Here's another example in which we have water acting as a Bronsted-Lowry acid and donating a proton to ammonia, which is the Bronsted-Lowry base. The hydroxide group becomes the conjugate base of the water, and the ammonium cation is the conjugate acid of the ammonia. Strong acids have weak conjugate bases. Weak acids have strong conjugate bases, and vice versa. This will be important in Unit 8. So let's summarize. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. In aqueous solutions, water can play an important role in many acid-base reactions because it can be a proton acceptor and it can be a proton donor. It is amphoteric. When an acid or base ionizes in water, the conjugate acid-base pairs can be identified, and we can compare their relative strengths.